Okay, hello everyone. So last time we proved that Ramsey numbers R and R, let's say, they are less than or equal to 4 to power R over root R. So we proved the upper bound for the Ramsey numbers is exponential. Now today, or our next goal actually is to prove the lower bound is also exponential, and to do that we want to get into the probability theory and probabilistic model. So the next goal is to derive a lower bound for the Ramsey numbers for which we use a probabilistic approach. And this probabilistic approach basically was originally used by Erdos approach. Okay, so let's look at probability theory. I'm sure you're familiar with probability theory and the basics from other courses, but let's just do a quick review about the basic concepts. So probability theory, when do we use probability, or what is probability space? So basically in probability theory, we always deal with a random experiment. So in probability theory, we have a random experiment that has certain possible outcomes. Okay, so it could be any random experiment. Each random experiment has some outcomes. It could be tossing coin or tossing dice, or other examples. The time that, let's say, you go to a bus stop randomly, and then you want to see how much time it takes or you should wait for the next bus. So the outcomes could be discrete or could be continuous. So in this course, we mostly focus on discrete random variables, or I'll define also random variables shortly, or the outcomes or the experiments whose outcomes come from a discrete set. So it has certain possible outcomes. The set of all possible outcomes is denoted by omega. So capital Omega is denoted by this and is called the sample space. So sample space is the set of all possible outcomes in a random experiment. Okay, so we have omega sample space, and then in probability theory we need to deal with events. So what was event? If you remember from your probability course, an event definition, an event is defined as a subset of the sample space omega, the set of all events is the set of all events under consideration is denoted by curly F. So when I say the set of all events under consideration, so if your set is a finite set, omega is a finite set, you can consider the set of, because any subset of omega is considered an event. So we can consider curly F to be set of all subsets of omega. Because omega is finite, the set of all subsets of omega is also a finite set, you know, it has how many elements? 2 to power number of elements of omega. And you can consider your curly F to be that. So if you have a finite set, then everything is straightforward and simple. But if you have an infinite set, or if you have a continuous set, like let's say a subset of real numbers, let's say omega is an interval, for example, then what can we consider as curly F? So then that is going to be defined in measure theory courses, you know. We can still say what curly F is or can be in that case, but because in this course we want to focus on discrete cases, so I don't want to go into details of, you know, measure theory and the case that omega is, let's say, an interval or a continuous set. So let me say in note in discrete case, F can be considered to be the set of all subsets of omega which has 2 to power number of elements of omega elements. Okay. So we are in the path of defining a probability space. So the basics that we need in order to construct a probability space. So it's a sample space, it's a set of all events. So omega and curly F. We also need to define a probability measure that is going to measure the likelihood of occurring occurring the events, likelihood of the events, likelihood of occurrence of events. So that is called probability measure. Let me give you the next definition. The probability, a function, let's say a function P from curly F to 0 and 1 is called a probability measure if it satisfies the following axioms. So the first axiom it should satisfy, but we want to define a probability measure, a function called probability measure that to each event assigns a number between 0 and 1. And what number 0 and 1? That number 0 and 1 is a number that measures the likelihood of occurrence of that event. So if it's 1, then that means certainly that happens. If it's 0, that means it's impossible to happen. Okay, so first of all, P of, so as we said here, so P of, let's say A has to be between 0 and 1 for any event A belonging to F, and P of omega has to be equal to 1. Okay, so just to emphasize, because when I say P is from F to 0 and 1, well, that means P of A is between 0 and 1 for any event A. But just to emphasize, I wrote it again. And the second axiom is that if, let's say, A1, A2 are countable number of pairwise disjoint sets or disjoint events. Pairwise disjoint events. What does that mean? Pairwise disjoint means AI intersection with AJ is empty for any I not equal to J. Or mutually exclusive. Sometimes we say pairwise disjoint sets or mutually exclusive events. This is the more common notation. Let me say pairwise disjoint sets, also called mutually exclusive events. And the meaning of pairwise disjoint sets or mutually exclusive events is that AI intersection AJ is empty set for I not equal to J. If we have such events, then probability of union AI, let's say from 1 to infinity, is equal to sigma P of AI, I from 1 to infinity. Of course, in the case that you have infinitely many number of AIs, if you have finitely many of them, then you can say I equals 1 to n, and then sigma PAI, I from 1 to n. Okay, so now we defined omega, curly F, and P. So these three together is called a probability space. So definition, any triplet omega, curly F, and P as defined above is called a probability space. Okay, so we know what a probability space is now. Now let's look at an example, a simple example. Let's say, so first we need, again, remember the process. We started with a random experiment. Then we defined omega, set of all, call this sample space, set of all possible outcomes, curly F, set of all events under consideration, and function small p, probability measure. Okay, so let's say if I define, so random experiment, let's say is tossing, random experiment. Let's say tossing a coin 3 times. Then what are the set of all possible or it's a fair coin. Fair coin means the probability that you observe heads or tails are same. So what are the set of all possible outcomes? So omega can be, so when you toss a coin 3 times, you can observe head, 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 or head, head, tail, and all the way to tail, tail, tail. So omega has 8 elements. And let's say F is, I define it as 2 to power omega, which is, as you know, the notation for a set of all subsets of omega. Okay, so 2 to power omega is the notation for the set of all subsets of omega. So F has how many elements? F has 2 to power 8 elements. And you also need to define probability measure. How can we define probability measure? So P of A, we are going to define it as number of elements of A divided by number of elements of omega for any A in omega. So for example, if A is, let's say, head, 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 tail, 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 and P of A is equal to number of elements of A, which is 2, divided by number of elements of omega, which is 8, or 1 over 4. Okay, so note here, the model above, where P of A is number of elements of A over number of elements of omega, is called the uniform probability space. And of course can be used in discrete case, and because we're talking about number of elements of A and number of elements of omega. If omega is an interval and A is an interval, then we cannot define it that way. But for discrete case, we can use it. And also fair experiments. So for example, fair coin or fair toss, fair dice, then we can use this model. Okay. Now the next thing that we need is random variables. So what is a random variable? Or before doing the random variable, let me give another example. Let's say consider a red-blue coloring of the complete graph K5, where each edge is randomly colored as red or blue. With no bias in coloring. Okay, so if it's unbiased, then we can use the model that we just said. If it's discrete and unbiased. So here's discrete, you know, you have finitely many edges in K5, and you want to color each of them randomly, blue or red. And let's say we are interested in finding, so let's say find the probability that exactly one edge is red. Okay, so okay, what is omega here now? So when we color, you know, the edges, so see we have K5 and okay, 2, 3, 4, 5, and then we randomly color this. Let's say this one, for example. And so what are the possible outcomes here? So how many possible outcomes do we have? See, this one that I sketched here is just one outcome, right? So this is one of the outcomes, one of the outcomes of our experiment, random experiment. So how many outcomes do we have in total? So how many edges do we have? First, let's look at how many edges. So CK5, note K5 has 5, choose 2 edges, which is 10. It's 10 edges. Now we want to color each of these edges randomly, blue or red. Okay, so how many possibilities do we have here? So for example, if I call them edges, edge 1, edge 2, edge 3 to edge 10. So for edge 1, I have 2 possibilities, either red or blue, right? So omega is equal to the set of all possibilities, possible outcomes, and number of elements of omega is 2 to power 10, because for each edge we have 2 possible outcomes, either red or blue. So that means, you know, by product rule, 2 to power 10 possible outcomes in total. Well, you know this, right? That if you want to do, let's say, two tasks, for first task you have m options, and for second task you have n options. In total, you have m times n options. So here we have 10 edges. For each edge, we have 2 options. So in total, we have 2 times 2 times 2, all the way times 2, so 2 to the power 10 options. Okay, so omega has 2 to the power 10 elements. So what is the event now? The event is that, so let's read the question again. So we have a K5, we're coloring it randomly. It says, find the probability that exactly one edge is red. So we are interested in the event. We know that each event is a subset of omega. Now, which event are we interested in to find its probability? The event where exactly one edge is red. So the event is the elements of omega where exactly one edge is red. So, for example, if I want to show one of them to you, see, this is one of them, for example. See, one edge is exactly red, or could be, and also, of course, I have to complete the other parts, other edges. So this is one of them, or it could be, let's say, okay. So these are two of the outcomes in omega where they are acceptable for us, because each of these two outcomes have exactly one red edge. Okay, so how many elements are there in this event? This event includes how many elements? So see, I have 10 edges in total. I want to consider one of them to be red, and the rest have to be blue. So 10 choose one elements are here, and so P of A is equal to elements. So P of A is equal to number of elements of A over number of elements of omega, because, of course, this is true again. Let me say uniform, we call this uniform probability space. Applicable if in unbiased discrete experiments. So we said that if you have unbiased experiment and it's discrete, we can use this formula. And then P of A is equal to 10 choose 1 divided by 2 to power 10. Okay, so that 10 choose 1 elements in A because I want to consider the red color for exactly one edge. So I have 10 choose 1 options for that, and then remaining 9 edges would be automatically blue. Okay. Now the next definition, random variables. Random variables, let omega be a sample space. Let omega be a sample space. A function, let's say capital X from omega to R, is called a random variable That's it. A function x from omega to r is called a random. So any function from omega to r is called a random variable. So what does a random variable do? Well, remember omega consists of all possible outcomes of our random experiment. Now, these outcomes may not be numbers, may not be real numbers. So for example, we saw they could be head, 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 or head, head, tail, right? So these are not numbers. So random variable assigns numbers to each of our outcomes. So it assigns the numbers to head, 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 assigns a number to tail, 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 right? So, and we are allowed to assign any real number. So of course, one easy way to, there's many times there are easy ways to assign numbers to our outcomes. So for example, to head, 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 we can assign 3, and to tail, 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 we can assign 0 if we want to assign numbers by counting number of heads, let's say. So one way to define random variable is to just count the number of heads, let's say in this experiment, and then assign numbers. So of course, that's one way to do it, one legitimate way to do it, but we don't have to. We can assign, for example, minus 500 to head, head, head. We are allowed to do that because we are saying that any function capital X from omega to R is a random variable. So if we assign minus 500 to head, 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 still is a function from omega to R and still is a random variable. Okay, so for example, in the example of tossing a coin 3 times, we can say capital X of omega is equal to 2 times number of heads in omega plus 1 for any omega in omega. Okay, so if I toss the coin 3 times, each possible outcome has some number of heads. So for example, head, head, tail has 2 heads, right? So the number that I'm going to assign to that outcome is, first I count the number of heads, then I multiply with 2, then I add with 1. This is going to define a random variable for me, because the domain of this function is all possible outcomes and the range is some subset of real numbers. But in this case, even subset of natural numbers. So still, of course, it's fine. Okay, so for example, x of head, tail is 2 times 2 plus 1, because number of heads is 2 here, which is 5, or x of, let's say, tail, the number of heads is 0, so 2 times 0 plus 1, which is 1, and so on. Okay, now let's look at a few, we want to look at a few important random variables. But before that, let me also give you a definition here. Definition, if x from omega to r is a random variable, then x equals a for a real number a is the event is defined to be the event. So see, x equals a, we are going to define it as the event omega in omega, such that capital X of omega is equal to a. Look at the right-hand side of this equality. It's obviously a subset of omega, capital omega, right? Because we're saying all elements, small omega and capital omega, that have the property that capital X of those elements is a. Remember, capital X of any element in omega is some real number, right? So we are going to pick all elements in capital omega, but where capital X of those elements is a. So this is going to be a subset of capital omega, and therefore it will be an event. Now, capital X equals a is defined to be this event. So capital X equals a is an event. Okay, similarly, capital X bigger than equal to a, or capital X bigger than a, or capital S less than equal to a, or capital X less than a are events. So for example, capital X bigger than equal to a is defined to be the event omega in omega, all omega in omega, the set of all omega in omega, such that capital X of omega is bigger than equal to a, and so on. So let me give you an example. In example above, say in example star above, let's call this example star. Okay, see, we defined the random, we had a random experiment, which was tossing a coin 3 times. We defined a random variable. How did we define random variable? We said, count the number of heads, multiply with 2, add with 1. Okay, so let's look at, for this experiment and this random variable, an example star above, let's say find the event, let's say capital X equals 2. So we just said that capital X equals 2 is defined to be an event. Event means a subset of omega, right? So what is capital X equals 2? capital X equals 2 is defined to be the set of all omega in omega with the property that capital X of omega is 2. So you have to tell me capital X of which elements in capital omega is 2. Let's look at the example again. See, for example, capital X of this element is 5, or capital X of this element is 1. Capital X of which elements are 2? The answer is no element, because capital X of any element is defined to be 2 times an integer plus 1, which is always an odd number. It cannot be equal to 2. So this is equal to empty set, because capital X of any element is 2 times some number plus 1, which is an odd number. What about capital X equals 3, let's say? Capital X equals 3 is the set of all omega in omega such that capital X of omega is 3. Now, capital X of which elements are 3? The output of capital X is 2 times number of heads plus 1. If you want 2 times number of heads plus 1 to be 3, number of heads has to be 1. Okay, which elements has number of heads equals 1? Well, one of them is head, tail, tail. One of them is tail, head, head. Tail, tail, head. And what else? Tail, head, tail. Okay, so that's it. So note here, since X equals A is an event, we can talk about probability of capital X equals A. Or similarly, probability of capital X bigger than A, and so on. Okay, so for example, in example above, so what is probability of capital X equals 3? Well, we just said that capital X equals 3 is this event. So this is equal to probability of head, tail, 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 head, tail, and tail, tail, head, which is the number of elements of this event, which is 3 divided by number of elements in omega, which is 3 over 8. Okay. All right. Now we want to look at some important random variables. Important types of random variables. Of course, we are looking at the discrete case right now. Okay, so what are the important types of random variables? So one important type is a binomial random variable. Okay, what is binomial random variable? Let's say, first of all, the notation is X binomial, let's say N and P. So it has two parameters. The binomial random variables, I can also say here with parameters N and P. Notation is this. So when do we have such random variable, or how is it defined? So if or suppose we repeat a random trial n times, each time with probability, let's say in n times, and in each time and in each trial n times independently. So we repeat a random trial n times independently, and in each trial we have two possible outcomes with two possible outcomes called the success and the failure with probabilities P and Q equals 1 minus P respectively. Okay, so what are the possible outcomes here? We are basically repeating it trial n times independently. Each time we have two possibilities called success and failure with probabilities P and 1 minus P. Of course, P has to be between 0 and 1 here. Okay. So this P, of course, is different from the probability measure. So this is just a number between 0 and 1. So we have n trials, doing them independently. Each trial has two possible outcomes. We call them success and failure. So it doesn't have to be really success or failure. It's just two outcomes. We're just calling it success and failure. As long as you have two outcomes, we are fine. Okay. So for example, it's a very standard example is tossing a coin because you have two outcomes, heads or tail, and then let's say you repeat it 5 times independently. If you toss a dice, then you have 6 outcomes, right? So then it doesn't fit into this situation, this scenario, unless you divide that 6 outcomes into 2 outcomes first. So let's say we can say odd number or even number. You can call odd number success, observing odd number success, observing even number failure, or the other way. So it doesn't matter which one you call success or failure. So as I said, success doesn't have to be really success. So for example, it's in lottery, you can say if I win, you either win a lottery or will not win a lottery. So you can call winning a lottery failure. Doesn't matter, just two outcomes. It has to be two outcomes. So one of them we call success, one of them we call failure. Okay, so omega is going to be the set of all possible outcomes. So one possibility is that, we have all successes or we can have one failure, or we can have two failures, and so on, or we can have all failures. Okay, so this is our omega. Now define x from omega to r to be x of omega is, let's say, number of success number of successes in omega. Okay, then we can say that probability of capital X equals, let's say, K is equal to N choose K, P to power K, and then Q to power P to power K, or 1 minus P to power N minus K, which is same as N choose K, P to power K, Q to power N minus K. Okay, and for K between here, for K between 0 to N. Okay, so if you want to have K successes, well, each success happens with probability P. So first of all, we have N trials in total. So if you want to have K successes, so first of all, we can choose the location of those K successes. It's going to be first and second, and let's say fifth. So we have to choose K locations out of N locations that we have in total. For each trial, I'm going to consider one location. So I have N, you can also see it here. I have, let me show you here. So first location, second location, and so on. Let's say if you want to have one failure, so that one failure can happen in the first location, second location, or the last location, let's say. Let's say similar if you want to have two failures, so two failures can be first and second, it could be first and third, or second and third, right? So I have to choose two failures out of, or two, if I want to have K successes, I can choose K locations out of N possible locations. For that one, I have N choose K options. And once I choose the locations or fix the locations, then for each location, the probability of success is P. So P to power K for that. And then I have N minus K remaining locations. And for them, for each location, I have probability 1 minus P for failure. So 1 minus P to power N minus K comes from there. Okay. All right, so another important type of random variable is Bernoulli random variable, which is a random variable with outputs 0 and 1 with probability P and Q equals 1 minus P respectively. Similar to previous situation, but previous situation, I repeated a trial, and each trial had two possibilities. I call them success and failure, but then I was repeating them n times independently. Now this one, we are not repeating the trial, just one trial and two possibilities. We're calling the outcomes P and one, and again, you can call them success and failure, and the probabilities are P and 1 minus P. And another type of random variable is called indicator random variable. So let's say A be a subset of omega, then the indicator random variable corresponding to the set A denoted by 1 sub A is defined as follows. So random variable is a function C1A, like any other random variable, is a function from omega, capital Omega to R. Remember, any function from capital Omega to R is called a random variable. Now, how is this function is going to be defined if you want to call it indicator random variable? The formula will be as follows. So 1A on omega, small omega is going to be defined as 1 if omega is in A, and it's going to be 0 if omega is not in A. Okay, so for example, again, if let's say an example of tossing a coin 3 times. Let's say if I set A to be head, tail, tail, head, head, tail, then 1A of head, tail, tail is 1, 1A of head, head, tail is also 1, but 1A of anything else is 0. Because A has only 2 elements, 1A, the indicator random variable on these 2 elements act to be 1, act as 1, and on everything else gives 0, assigns 0 to everything else. So 1A of, for example, head, head, head is equal to 1A of tail, head, tail, 1A of tail, 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 and other elements, they're all 0. Okay, so these are important random variables. So of course there are other random variables, discrete random variables like geometric random variables, Poisson random variables, but I'm trying to focus on the ones that we frequently use in this course. Okay, so one remark here, example we did above for red blue coloring of K5, it can be considered as an example of, so which type of random variable do you think we actually had in that example? If you remember, we did an example where we had K5, we did the red-blue coloring of edges, we had 10 edges in total, and then we looked at the probability that exactly one edge is red. See, what were we doing? We were coloring 10 edges independently. So this is basically, you have 10 trials, and each trial you're doing it independent from others. And for each trial, you had two possibilities. Either you had to color it with red or blue. So it exactly fits the binomial random variable. Each trial we had two possibilities. So here we call it red and blue. We could call it success and failure. And the probabilities, we call them small p and 1 minus p. Well, here, because we said randomly and unbiased, basically, we just consider each probability to be 1/2, because there's no bias for red in favor of red or in favor of blue. So each probability we consider 1/2 for each edge. Okay, so it was an example of a binomial random variable with which parameters? With parameters n was 10. N is the total number of trials. There was trials. Each trial basically was coloring an edge, one edge. So we had 10 edges, so 10 trials, and P was the probability of success in each trial. In each trial, the probability that we color it with red or blue, each one is 1/2, so P is 1/2. And X was, okay, so basically X is binomial 10 and 1/2. And we found, so if I want to say in the language of random variables, we find the probability of one edge. If you remember, probability that we asked about what's the probability that exactly one edge is red. So we asked for probability that X is equal to 1. So here X denotes, or X sub, let's say any omega, is number of red edges in omega, right? So here success is observing red edge. Because we said X number of successes, here is number of red edges. So that means our success basically is observing red edge. Okay. All right. The other things that are very basic and important in probability is expected values, right? So expected values. What is the definition of expected value? Again, remember that we are in discrete case, so we can skip, measure theory and integration and all these things. So because discrete case, we just have a sum. So definition, let X be a random variable. The expected value of X denoted by E of X is defined as E of X is defined as sigma small x, and then P of capital X equals, I can write it as, let's say, just to make sure they are not confused with each other. I can say sigma A P of capital X equals A. The sum is over A. The sum is over all possible outputs of X. So this is how the expected value is defined. So let's look at an example of expected value in the case of indicator random variable. Example, let's say if capital X equals 1 sub A. So what is expected value of X then? Expected value of X equals expected value of 1A. So it's going to be, what are the possible outputs? Because we have to sum over possible outputs of capital X. Now, if you remember, if capital X is 1A, 1 sub A, it had only two outputs. Remember, random variable is a function. It has some outputs. In the case of 1 sub A, it has only two outputs. So let me show you. See, it had only two outputs, either 1 or 0. 1 if omega is in A, 0 if omega is not in A. So we are going to have 1 times P of X, let me say P of 1A equals 1 plus 0 times P of 1A equals 0. Well, 0 times anything is always 0. So this is P of 1A equals 1. But what is 1A equals 1? Remember, capital X equals A is an event. Is an event containing all elements in omega that are going to be mapped to A. So all elements in omega here that are going to be mapped to 1. This is probability of all elements in omega such that 1A of omega is 1. But 1A of which elements are 1? 1A of elements in A are 1. And 1A of elements outside of A are 0, right? So this is exactly P of A. See if I can show you also here. See if this is, let's say, omega, and let's say this is A. So these elements here are going to be mapped to 1, and elements here are going to be mapped to 0. So if I want to see which elements in omega are mapped to 1, which is exactly this set here, all elements in omega that are going to be mapped to 1, well, only elements in A are mapped to 1. So this set here that you can see, I'm showing with the cursor, is exactly A. So P of this means P of A. Okay. All right. So this is one example, and another example. Let's say for X, if it's binomial random variable with parameters N and P, then what is E of X, or expected value? Expected value of X is sigma A P of X equals A sum over A. So what are the possible outputs of X binomial N and P? If you remember, the possible outputs was, we said P of X equals K. We gave the formula for K greater than equal to 0, less than equal to N. For everything else, P of X equals K would be 0, of course. So the possible outputs of X is either 0 or 1 or 2 all the way to N. So this is going to be 0 times P of X equals 0 plus 1 times P of X equals 1 all the way to N times P of X equals N. So this is 0 times P of X equals 0 means N choose 0, P to power 0, 1 minus P to power N minus 0, plus 1 times N choose 1, P to power 1, 1 minus P to power N minus 1, all the way to the last one is N. P of X equals N is N choose N, P to power N, 1 minus P to power N minus N. So it can be shown that that this is NP. So E of X is NP. Now note here that E of X is also called the first moment of random variable X. Now similarly, second moment can be defined. Now definition, if X is a random variable, E of X squared is defined to be the second moment of X and it can be shown that E of X squared is equal to sigma A squared P of X equals A. Again, the sum is over all possible outputs of capital X. Now, one remark here is that note, if capital X is a random variable and if capital X is a random variable and let's say G from R to R is a function, then capital Y equal G of capital X is also a random variable. Okay, remember any function from omega to r is called a random variable. Now, if capital X is a random variable, g of capital X for any standard function g is also a function from capital omega to r, and therefore that is also a random variable. So for example, again, if let's say we say x of omega equals 2 times number of heads plus 1. Remember we did this example above. I think I called it example star above. Then let's say if I consider a standard function, you know, like high school function, let's say set g of x equals e to the x, for example. Then I can say that capital Y equals g e to the capital X is a random variable and for example capital Y of, let's say, head tail tail. What is how, because when we have a random variable that means we have a function from omega to r. Now let's say capital Y of HTT. What is that going to be according to the definition? So it's also a random variable. I can also explicitly say that what type of random variable it is, or what is the formula for this random variable. Is a random variable given by or defined by capital Y of omega is equal to G of capital X of omega. So this is the way that capital Y of omega is defined. Now here, for example, capital Y of this omega, small omega, is defined to be, how is it defined to be? Capital Y of HTT is defined to be e to power capital X of HTT, and capital H of HTT is 2 times number of heads is 1, so 2 times 1 plus 1 is 3, so e to power 3. Okay, so capital X squared itself here is also a random variable, and e of x squared can be calculated because e of x is already defined for any random variable. So we can use that original definition, or it can be shown that e of x squared can be calculated this way. Okay, so another definition is for variance, the variance of a random variable x is defined as the variance x is defined as expected value of capital X minus mu the whole squared. Now this is your capital Y equals note capital Y equals capital X minus mu the whole squared, and here mu, by the way, is e of x, expected value, is a random variable. So we can find, let's say capital X is given, we find mu, expected value of x. Capital X minus mu is a random variable. Capital X minus mu the whole squared is also a random variable. We have a new random variable. Let's call it capital Y. E of that expected value of that random variable is called variance x. And it can be shown that variance x is expected value of x squared minus expected value of x squared. Okay. And what does variance show? Basically, variance shows how focused your data is around mean. So if let's say all the data, let's say is a constant function. Let's say all the outputs are same. Or let's say if we have a, for example, exam where all the students got the same grade, then variance is 0 because they're all focused around one point. And as variance increases means the data is less and less focused around the mean. Okay. All right. And some other properties that we need in this course. Some more properties of probability measure or probability space. Probability spaces. So one is that probability of A complement is 1 minus probability of A. Here, A complement or AC is complement of A. Second one, probability of union of AI, I from 1 to infinity, let's say, it's less than or equal to sum of probability AIs. So if you remember one axiom was that probability of union AI is equal to sum of probability AIs if AIs are pairwise disjoint. But if I remove that condition, well, that equality becomes less than or equal to. So for any events A1, A2, and so. Another probability of A, let's say 1 intersection A2. So this is multiplication of, so P of A1 times P of A2 times P of AN if A1 to AN are independent events. So this is actually one way to define independent events. If P of intersection is multiplication of probabilities, then we call that those events independent. Fourth one, probability so we can also look at, for example, probability A union B. So that's also a famous formula. Probability of A union B can be defined in terms of P of A and P of B. Probability A union B is equal to P of A plus P of B minus P of A intersection B. Fifth property called Markov inequality It says if X is a non-negative random variable, so non-negative random variable means what? Means X is a random variable from omega to 0 to infinity. Remember that when we have a random variable means we have a function capital X from omega to R. Now, if I have a function from capital omega, not to whole R, just to 0 to infinity, then I call that random variable a non-negative random variable. So non-negative random variable means all the outputs of capital X, which is a function itself, are non-negative. So if X is a non-negative random variable and if T is greater than 0, then probability of X bigger than T is less than or equal to E of X over T. Okay. And sixth property, a Chebyshev inequality. Now for this one, X can be any random variable if X is any random variable. Then probability of capital X minus mu bigger than equal to K sigma is less than or equal to 1 over K squared. So this is one way to express Chebyshev inequality. So what does these two inequalities, look at these two inequalities. Well, these are true for any, of course, Markov for any non-negative random variable and Chebyshev for any random variable. So we are not specifying whether we need, for example, binomial or Bernoulli or whatever. So any random variable can be replaced here for these results. Now, what are they saying? So for example, look at this one, probability of absolute value X minus mu bigger than K sigma is less than 1 over K squared. So what is it saying? So it's absolute value X minus mu. So let's recall from high school that when we say absolute value, let's say A minus B, we are talking about distance between A to B. So it says that the probability that the distance between X and mu is bigger than K sigma. Let's say if K is a big number, K sigma will be also a big number. So by the way, here, sigma is square root of variance X that we defined above is called the standard deviation. Standard deviation. Okay, so let's say if K is a big number, then K sigma is also a big number. So it means that the probability that the distance between X and mu is a big number is less than 1 over K squared. If K is big, 1 over K squared will be small. So the probability that the distance between X and mu is big is very small, or has to be very small. It's less than 1 over K squared. So let me show you here. So for example, if K is, let's say, 100, okay? So then that means probability that absolute value X minus mu bigger than 100 times sigma is less than 1 over 100 squared. Okay, so what does that mean? What does that mean? This means the probability that X is very far from mu, from the average, mu is very small number between 0 and 1/100 squared. So when I say very far here, again, remember absolute value x minus mu shows the distance between x and mu. So the probability that the distance between x and mu is bigger than 100 sigma is a number between 0 and 1/100 squared, which means a very small number. So that means x and mu cannot be very far from each other, because the probability that the distance between them is very large means that the probability that they are very far from each other is very small. So when I say very far here, so here by far we mean their distance is at least 100 times sigma, because absolute value x minus mu again shows the distance between x and mu. So in other words, with high probability, x must be close to its average. So how high and how close, but they depend on each other. Yeah, okay, so there are also, other inequalities as well that we will use in this course, but these are basically the basic ones that we are going to frequently use. And as an exercise, by the way, you can also try to interpret Markov inequality in the way that I interpreted the Chebyshev inequality. Okay, so these are the preliminaries that we need from probability. So we are going to use them next time to derive results in Ramsey theory. Okay, so hopefully this was a quick review for you that, we probably saw this in other courses, but maybe reminded you about them, these basic facts. Okay, so see you next time. Thank you.